In Chapter 8, we're going to discuss the quantum mechanical model of the atom. We'll do this by talking about light, since characterization of light gives us a lot of insight into how electrons are arranged in an atom. From there, we'll discuss the different theories of how the atomic particles are arranged. In each section of material, I'll present the learning goals of the authors. You'll want to make sure you're reading and studying so that you can accomplish these broadly defined goals for each section. After the author's goals, I'll present the learning outcomes I specifically want you to achieve. These are based on Bloom's taxonomy of learning and may be something as simple as define a term, or they may be in-depth enough that you have to pull together multiple concepts to synthesize an answer. Anytime you see the word recall, that means we expect that you've learned this material in Chemistry 109. This section is fairly lengthy, so I've split it into 2 lectures. Let's begin. In its most basic definition, light is a form of energy that can be described as a moving wave of magnetic and electrical potential. Visible light is the only type of light that can be perceived by the human eye. Light can be described as a wave because it, 1, travels through space, and 2, can be refracted or have its direction changed. Light has several important physical dimensions that we can measure. The wavelength, lambda, is the distance between 2 corresponding points on a wave. Here, we've measured the wavelength between 2 troughs. The amplitude, or height from the midpoint of the wave to its crest or trough, is related to the brightness or intensity of light. Higher amplitude waves will appear brighter. Constructive interference occurs when waves are in phase, causing their amplitudes to add together. These lead to brighter areas on a screen when waves from a light source travel through an opening and are diffracted, or spread out as a result of traveling through a narrow slit. Destructive interference occurs when waves that are precisely out of phase add together, canceling out all the peaks and valleys. These are the dark spots on the screen. Frequency, nu, is the number of crests that pass a given point per second. The unit is seconds to the -1, which can also be called inverse seconds or hertz, abbreviated Hz. When we multiply the frequency in hertz and the wavelength in meters, we get a fundamental quantity, the speed of light, which is about 3 × 10⁸ meters per second. The electromagnetic spectrum covers a wide range of wavelengths and frequencies. We see that longer wavelengths, such as radio waves, have lower frequencies and lower energy. Shorter wavelengths have higher frequencies and higher energy, such as the X-rays that are energetic enough to pass through our bodies to give images of our bones. To give you a feel for the range of wavelengths and frequencies we're talking about, I've copied this table from the text. Please, do not memorize this information. Rather, I want you to focus on remembering the order of increasing frequency or decreasing wavelength: radio, micro, IR, visible, UV, X-rays, gamma rays. To help, I've listed some of the more popular mnemonics here. The portion of the electromagnetic spectrum that we can see is actually very small and ranges from about 380 to 700 nanometers. Note the colors we see start with the shortest wavelength and the highest energy: violet, then indigo, then blue. The mid-spectrum colors are green and yellow. Then we wind up with the highest energy, shortest wavelength, orange, then red. Here's a problem for you to try. If you need to, go back to the last slide so you can label these visible light waves in terms of wavelength, frequency, and energy. Here are the answers to all 3 questions. If you got any wrong, please review your logic to find your error. At the end of every lecture, I'll also leave you with the parting thoughts of the authors. These are the topics for review for material we just covered.